Hello students, this is the fourth online class on group theory. So in this class, I'll be teaching you the kernel of a homomorphism. So kernel of a homomorphism is you have a function f from g to g dash where f is a homomorphism and e dash is the identity of g dash. Then you take a subset k of g defined by k is equal to a belonging to g such that f of a is equal to e dash. That is, those elements which are mapped to e dash, that set is called as k, and this is a subset of g, and this subset k is called as the homomorphism of f, and it is denoted by kernel of f. So what is a homomorphism? Homomorphism is if you have a function f from g to g dash and g has the operation circle and g dash has the operation star, then f of a circle b is equal to f of a star f of b. So here kernel of a homomorphism means you're taking those elements, say in this diagrammatic explanation, when I explain this using the diagram, this shows that those elements here E, A, B and C are mapped to identity. So these elements belongs to kernel of F. So those elements which are mapped to identity are called as kernel of the function F. And kernel of F is always non-empty because identity is always mapped to an identity element. So let us look at the theorem. You have a function f from g to g dash being a homomorphism. Then from the group g to g dash with kernel k, then k is a normal subgroup of g. So to show that k is normal, there are two conditions to be proved. That is, k is a subgroup of g, and for all k belonging to k, gk g inverse must be an element of k. So since we already know that k is non-empty, that is E will always be in k is a non-empty set. So we take two elements A and B in k. So we need to show that AB inverse also belongs to k. So we have from the definition of kernel that f of a is equal to e dash and f of b is also equal to e dash. So we consider f of AB inverse. This is equal to f of a into f of b inverse, since f is a homomorphism, and f of b inverse is nothing but f of b the whole inverse. So f of a is identity and f of b is also identity. So you get back the identity element. So you have f of ab inverse is equal to identity. That means that ab inverse is an element of k. So therefore k is a subgroup of g. So the next thing to prove is k is normal in g. That is, to prove that GKG inverse belongs to K. For that, we need to show that f of GKG inverse is equal to E. So to prove that, we consider f of GKG inverse. This is equal to f of G into f of K into f of G inverse, as f is a homomorphism. So this is equal to, as K is an element of K, f of K is nothing but identity. And this is equal to f of GG inverse. GG inverse is identity as G is an element of G. So f of E is equal to E dash. So therefore we can say that GKG inverse belongs to K for all G belonging to G and K belonging to K. Hence K is a normal subgroup of G. Now let us look at the next theorem. Let f from G to G dash be a homomorphism from group G into G dash with kernel K. Then f is 1, 1 if and only if K is equal to singleton identity, where E is the identity element of G. So here you have an if and only if condition. So if we first assume f is 1, 1 and show that K is equal to singleton identity, and the next is K is equal to singleton identity and we show that f is 1, 1. So to know what is a 1, 1 function, we look at we'll look at the definition of a 1, 1 function. That is, so you have a function f from a to b, then f is said to be 1, 1 if every element of a is mapped to a unique element of B, then we say that f is a 1-1 function. All the elements of A must be mapped to a unique element of B. So the condition is f of A is equal to f of B implies A is equal to B. If we show this condition, we can say that f is a 1-1 function. Now we'll look at the proof. So here we first assume that f is a 1-1. If f is 1-1 means f of x1 is equal to f of x2. This implies x1 is equal to x2 where x1 and x2 belongs to G. Now we need to show that K is a singleton identity. So let us consider an element of K. Let A belongs to K. This implies f of A is equal to E dash from the definition. So this is equal to f of A is equal to E dash is nothing but f of E, I can write, because identity is also mapped to identity element. Since f is 1-1, I can say that A is equal to E. Therefore, K is equal to singleton identity. So for any A in K, we have shown that those element A is equal to identity. Now conversely, let K is equal to singleton identity. Now we need to show that if f of A is equal to f of B, I need to show that A is equal to B. For that, I multiply both sides from the right hand side with f of B inverse. So this is equal to f of A into f of B inverse is equal to f of B into f of B inverse. And since f is a homomorphism, I can write it as f of AB inverse is equal to f of BB inverse. And BB inverse is equal to identity as B is an element of G and G is a group. So f of E is equal to E dash. So AB inverse is equal to E. The reason is AB inverse belongs to K. If f of AB inverse is equal to E dash means AB inverse is an element of K. And since K is singleton identity, AB inverse is equal to E. So multiplying right side but B, we get this as A is equal to B. Therefore, F is 1-1. Next, we'll go to the next theorem. Let G be a group and H be a normal subgroup of G. Then G by H is a homomorphic image of G with H as its kernel. So let us see what is a homomorphic image first. If suppose you have an example as f from z to z is a function given by f of n is equal to 2n. So these elements are mapped to even integers. So this set is f of z. All those images you call it as f of z, and this f of z is called as the homomorphic image of z under the condition that this f is a homomorphism. If this f is a homomorphism, then this set f of z is called as the homomorphic image of z. And see here, f of z is a subset of z here because you have other elements 1, 3, 5 and 7 and so on. All the odd numbers are there still, or odd integers. So this f of z is a subset of z. In fact, this f of z will be a subgroup of z also. So remember that all the images of z under this mapping is called as the homomorphic image under the condition that this f has to be a homomorphism. Now let us look at the proof. So to show that this G by H is a homomorphic image of G, we need to define a map. So I define a map f from G to G by H as f of x is equal to hx for all x belonging to G. I need to show that f is a homomorphism and its kernel is H. So we have from the definition, we know that f is well defined. F is well defined means every element of G is mapped to some element of G by H, and also f is onto, since we know that every element is mapped to some coset. So clearly f is well defined and also f is onto. So consider f of xy is equal to hxy. Since from the definition we have hxy, and this hxy is nothing but hx into hy from the properties of cosets, and this can be written as hx is equal to f of x and hy is equal to f of y, we have f of xy is equal to f of x into f of y. Therefore, f is a homomorphism. So we need to find out what is a kernel now. The kernel of f is equal to x belonging to G such that the definition of kernel says all those elements of x, all those elements of G which are mapped to identity of G by H. So give such that f of x is equal to identity of G by H. So this is equal to x belonging to G such that f of x is nothing but hx and identity of G by H is nothing but H. Therefore, we have this as x belonging to G such that hx is equal to H means x belongs to H. So kernel of f is equal to H. Therefore, G by H is the homomorphic image of G with H as its kernel. So whenever you have doubt with the quotient group, right, you always look at this example which I have already explained in the previous class. Take the set group Z6 with subgroup as H is equal to 0, 3 and write down what is G by H, and whenever you get a doubt about quotient group, always look into that example and clarify it. Therefore, G by H is a homomorphic image of G with H as its kernel. So this is nothing but these are all the images of G. So since F is homomorphism, you call this as a homomorphic image, and we have shown that kernel of F is nothing but H. Now let us look at the next important definition, that is isomorphism of groups. F is said to be an isomorphism if it satisfies three conditions, that is F is 1, 1, on 2 and homomorphism. If these three conditions hold good, then you say that F from G to G dash is a isomorphism, and we say that as G and G dash are isomorphic, and we write it as G isomorphic to G dash with this notation. And if suppose F is a function from G to itself, that is you have a function F from G to G and it is an isomorphism, we call those kind of isomorphisms as automorphism. So for example, you have a function F from I comma plus to 2i comma plus, where I is a set of all integers defined by f of x is equal to 2x. For all x belonging to I is an isomorphism, because this is an every element of I is mapped to an element of 2i. You can check that this 1, 1 onto and also homomorphism. So this is an isomorphism. F from G to G defined by the identity map. Identity map is it takes the elements to itself. That is I is a mapping from G to G itself, and this is an isomorphism. In fact, this is an automorphism because it is a mapping from G to itself. Now let us look at one of the very important theorem, fundamental theorem of homomorphism. This says that every homomorphic image G dash of a group G is isomorphic to some quotient group, or I can also write this as let F from G to G dash be a homomorphism of a group G into a group G dash with kernel K, then F of G is isomorphic to quotient group G by K. We have F is a homomorphism, so we have taken F from G to G dash is a homomorphism with kernel K. So F of G is a subgroup of G dash. Just make the little changes here. So F of G is a subgroup of G dash and hence a group by itself. So you're looking at this diagram, you can understand that G to G dash is a homomorphism, that is F, and G to G by K. We have already shown in the previous theorem that G to G by H, where G by H is the homomorphic image of G. So we can define a function G to G by K, and G by K is the homomorphic image of G. Also, F of G is also called as a homomorphic image of G by defining a function F. So we have F of G is also homomorphic image of G. So what we have to prove is that F of G and G by K are isomorphism. This is also a homomorphic image of G. Even this is a homomorphic image of G. We show that these two are isomorphic. And here we have that F of G is a subgroup of G dash. To show that these two are isomorphic, we define a map phi from G by K to f of G given by phi of Ka, an element of G by K is of the form Ka. This is equal to f of A for all A belonging to G, Ka belonging to G by K. So first we need to show that phi is well defined. That is to show that every element has an image. That is, if K is equal to Kb, then phi of K is equal to phi of Kb. That is, every element has a unique image. So consider K is equal to Kb. This implies that AB inverse belongs to K. Since K is the kernel, f of AB inverse is equal to E dash. And since f is a homomorphism, I can write it as f of A into f of B inverse is equal to E dash. Multiply both sides by f of B and we'll get it as f of A is equal to f of B. And since we have defined it as f of A is equal to phi of K and f of B is equal to phi of Kb, we can show that phi is well defined. That is, when you go the other way around, it shows that it is 1 1. So phi is 1 1 means phi of K is equal to phi of Kb. That implies f of A is equal to f of B. So under the same argument, if we show, we'll get this as K is equal to Kb. Therefore phi is 1 1. Now let us look at what is onto function. Onto function is, say you have a function f from A to B, then every element of B has a unique, every element of B has a pre-image, then that kind of function is called as an onto function. So here A has two pre-images, 1 and 3, B has a pre-image 2, C has a pre-image 4. So every element in B has a pre-image. But this function is not a 1 1 function, as 3 is also mapped to A, 1 is also mapped to A. So here the condition is, it does not satisfy, and even 5 is not at all mapped to any element. So f is not a 1 1 function, it is only an onto function. So the condition is, for every y in B, there must exist an x in A such that f of x is equal to y. That there should be a mapping x to y. Then we call that kind of function as an onto function. Now let us look at when is phi onto. So let B belongs to f of G. Since B is an element of f of G, and you know that f of G is nothing but the homomorphic images. That is, it contains all the images. So there exists an element A belonging to G such that f of A is equal to B. Now we know that there exists a Ka belonging to G by K such that phi of K is equal to f of A from the definition, and we have f of A is equal to B. Hence phi is onto. That is, for every element in f of G, we can find a Ka in G by K such that phi of Ka is equal to B. Hence phi is onto. The next what we have to prove is phi is a homomorphism. So consider phi of Ka into Kb. This is equal to phi of Kab by the properties of cosets, or by the definition of quotient group. So this is equal to f of AB by the definition, how we have defined the mapping phi, and this is equal to f of A into f of B, as f is a homomorphism. F of A is nothing but phi of Ka, and f of B is equal to phi of Kb. Therefore, phi of Ka, Kb is equal to phi of Ka into phi of Kb. Therefore, phi is a homomorphism. So we have checked that phi is homomorphism onto and 1 1. Therefore, phi is an isomorphism from G by K onto G dash or f of G. In case, if suppose G dash itself is f of G, then we can write it as G by K to G dash, or we can also write it as G by K to f of G. Therefore, G by K is isomorphic to f of G or G dash if f of G is equal to G dash. So this is a very important theorem on homomorphism, the fundamental theorem of homomorphism. So that's all for today's class. In the next class, I'll be teaching some of the problems based on isomorphism. Thank you.